So how can losses happen at the data link layer? At times the SNR is so low that you cannot even distinguish the signal from the noise. In other words, the noise dominates and thereby you cannot even recover any bit, in which case it results in a loss of packet. Also, a lot of implementations at the physical layer, when the physical layer detects that there is a corruption of packet, even though there are bit errors, at times it just drops the packet. It doesn't pass it to the data link layer. So that is an implementation artifact, but in general you have to deal with both errors as well as losses as part of the RDT protocol. Now that we are considering a channel with errors as well as losses, do you think this RDT version 2.1 works? So consider these two cases. In this case, the packet got lost. In other words, it didn't even reach the receiver, and the receiver, for all it cares, it didn't see any packet, so it doesn't generate any feedback. In this case, the packet reached, but the ACK got lost. In other words, it didn't reach the sender. In either case, the sender gets no feedback. Until now, whatever we have seen, the trigger for a sender to act is based on feedback. Now, when it doesn't get a feedback, what do you need? You need some other mechanism, basically. So you need a timeout mechanism. The question next is, how long do you wait? In other words, when do you retransmit the packet? So timeout means you are timing out after some time and then you are going to retransmit the packet. The question here is how long to wait? What should be the value of your timeout? So how long to wait? This is basically a function of the link characteristic. In other words, you have to wait for as much time as it takes for the packet to reach the other end and for the ACK to get generated and come back. So this will be in function of the transmission time of the packet and the ACK, the propagation time, the processing time, so on and so forth. So this is something that is a variable that needs to be adjusted according to where you are using this RDT. So let's call this new protocol with timeout the RDT version 3. As you see the required functionality, now I have added a timeout timer. So here in this case, the sender waits a reasonable amount of time, which is a configurable parameter for the ACK, and it retransmits if no ACK is received in this time. Now there is a possibility that the ACK just got delayed and not really lost, in which case this retransmission is going to be a duplicate, but we already have a mechanism to handle it, that of using sequence numbers. So here is RDT version 3 in action. So by the way, this protocol we have described so far is also called stop and wait protocol. It is also called alternating bit protocol because you alternate between the sequence number 0 and 1. That is why it's called alternating bit. So when there are no losses, things are rather straightforward. You send packet 0, the acknowledgement acknowledges packet 0, you send packet 1, you get ACK 1, so on and so forth. Now here is a case where the packet is lost. When the packet is lost, you are not going to receive any acknowledgement. Thereby you wait for some time, timeout, and then you are going to retransmit the packet. In response to this, you get an acknowledgement, and then again things go on as usual. So here is a case where acknowledgement is lost. Because acknowledgement is lost, the sender doesn't know the status of the packet. Thereby again it will time out and resend the packet. In this case, the packet happens to be a duplicate because the original packet itself reached the receiver. In this case, the receiver uses a sequence number to identify that this is a duplicate packet and it is going to discard the packet. But in spite of this, it still sends an ACK. Why do you think it should do that? So that the sender knows that this retransmission was successful. So here is the case for the premature timeout. In this particular case, you send packet 0. In response to this packet, you are sending an ACK from the receiver, but unfortunately this ACK got delayed. So what is happening at the sender is you timed out even before the reception of the ACK and you retransmitted this particular packet 0. Now when this duplicate packet 0 arrives at the receiver, what should the receiver do? Since this is a duplicate, it should definitely discard the packet, but the question is, should it send an acknowledgement or not? Well, it should send the acknowledgement because it is conceivable that this previous ACK was lost and this was a retransmission due to timeout, and thereby the sender needs to know that this retransmission was successfully received. Thereby it is important to send this acknowledgement. Note that the receiver doesn't know what is happening at the sender. Either this, whatever timeout happening, a premature timeout could have happened, or this ACK could have been lost and this was a valid retransmission. It cannot distinguish between these two cases. So it is important that this retransmit this particular acknowledgement so that the sender knows that this packet was successfully received. Now, once you receive the first acknowledgement here in the natural scheme of things, since it is acknowledging packet 0, you retransmit packet 1. This is straightforward. So the more challenging question is, once you receive this duplicate acknowledgement, what should the sender do? Should it retransmit this packet 1 again or not? So if you remember this case where it received this duplicate ACK resulting in corruption of the previous packet, you insisted that the packet 1 be retransmitted. So this is the earlier version, RDT version 2. Now based on that, you could insist that packet 1 be retransmitted because it is conceivable that the earlier transmission of packet 1 was corrupted. This could have happened and this ACK 0 was a result of that, though in this particular case it's a consequence of premature timeout. Again, as I said, the sender has no knowledge which of the two cases has happened. Either premature timeout has happened or whether the packet 1 was corrupted. So in this case, it could potentially send packet 1 again. But this results in a bug, and this bug is called the sorcerer's apprentice bug. What this bug is, why don't you continue this protocol operation and figure it out for yourself? There is something wrong if you actually retransmit this packet 1. I will cover more of this in the practice problem. So this is not the right behavior. In other words, you should not retransmit this packet 1. So that is what is mentioned here. I'm saying you should just ignore this duplicate acknowledgement and do nothing. This, I say, in RDT version 3 results in correct behavior of this particular protocol. Can you answer why? Because in RDT version 3, we have this timeout mechanism in place. Even if it were the case that this packet 1 was corrupted and this ACK was a result of that, even if you ignore it, it is okay, because after some time you can time out and retransmit this packet 1. So for example, you could time out here and decide to retransmit packet 1 in case it was a corruption. In case it was a premature timeout, by doing nothing, you are avoiding that sorcerer's bug. So this is the correct behavior to do. Again, lot of subtleties. Spend some time absorbing all this before you proceed further. So these protocols have to handle many challenges. They have to handle ACKs packets getting lost, they getting delayed. We didn't cover these because these are kind of rare in the link layer, but packets can get duplicated, they can get reordered. Your timeout values may not be set correctly and the receiver itself may not be capable of many things. In other words, the buffer space could be really small, its processing capabilities can be limited, and you have to design these protocols where the reliability has to work correctly and also this particular protocol has to work efficiently. What do you mean by efficiently? I'll cover it shortly, but these are the design goals of RDT protocols. So TCP is another reliable protocol which we will cover at later time, and this is even more complex than what we have covered so far. And to this day, even though I've studied TCP, there is something I realize about TCP which I didn't realize before. So these protocols are very subtle. So a lot of research goes on in them. So the debate of NAC versus ACK, I said I will address later. So here it is. So we saw earlier that we could eliminate NACs and just manage with ACKs. Earlier we saw that eliminating ACKs and just managing with NACKs doesn't work if the end system crashes. There are other problems also with this. Can you think of any other issues? So the way the NACKs work is they can conclude that packet loss has happened only on detecting holes. In other words, they received packet X and they received packet X plus 2. That means packet X plus 1 is lost. So that is how they detect holes. Now it is possible that some packets get sent and the next packet, this X plus 2 packet, gets sent after a really long time, after X. In which case, if this packet X plus 1 were to be lost, you are not going to recover it. And that's not a good thing to do. And there is another fundamental problem. What if the last packet of the flow itself is lost? Now the receiver doesn't know that it is the last packet, so it's not going to generate NACK, and the sender is going to assume all is well because it did not receive any NACK. So it's kind of a deadlock situation here. The one good advantage of NACK is if errors are infrequent, the feedback that you're going to provide is going to be very less. In other words, you provide feedback only when there is error. Now that we have designed this stop and wait protocol, our RTT version 3.0, let's see how well it performs in terms of throughput. So consider this case where you are trying to provide reliability between two nodes AB, and the link that is connecting them is a 10 Mbps link. It has a 10 millisecond propagation delay, and the packets that I am going to send on them are 1000 byte long. And assume that the ACK packet is too small that you can ignore its transmission time. Now what is the throughput I am going to achieve if I were to use this stop and wait protocol? So in stop and wait protocol, you transmit the packet. Now this packet has to go to the other end, then the ACK has to come. So basically you are sending one packet this much duration. So it's one packet every tx time plus round trip time. This round trip time is nothing but twice the propagation delay. So if you plug in the values here, so you're basically sending 8000 bits over, this is the transmission time plus twice the propagation delay. Everything I've converted it into seconds. So this, if you do the calculations, turns out to be 384.6 kbps. Now remember, the original link was a 10 Mbps link and all you managed to get was 384.6 kbps. So the utilization as such is only 3.8% of the link bandwidth. So it is extremely poor utilization. The same can be calculated this fashion also. So out of this whole time, the useful work that got done was just this much time. So the useful work is transmission time over transmission time plus RTT. For this entire RTT duration, the link was idle. So you wasted the resources. So this protocol is an extremely inefficient protocol. So if we are commending ourselves on a job well done in designing this RTT protocol, the performance shows that it's not a very good job. So we got the protocol correct, but we still did not achieve a very efficient protocol. So we need to better this protocol. So here is a summary of what we have learnt in this video. So reliable data transfer protocols provide an abstraction of reliable channel to the higher layers. So they in turn tackle unreliability. Now we have incrementally determined the required functionalities needed as part of this protocol. So we first considered only bit errors and then we added losses on top of it, and we saw that we need many functionalities: error detection, we need receiver feedback, we need sequence numbers, so on and so forth. The current protocol, while works correctly, it is still inefficient. So in the future, we are going to build on this framework. In other words, we will use all these functionalities that we developed, but we are going to make the protocol more efficient. So that's in the next video.